Hi everyone. This is going to be the first lecture in the Analog and Digital Electronics course. So those of you taking it at Stan State, that's the Phys, Phys 4250. So hopefully you're watching the right lecture. So this first lecture is going to cover the first three sections of chapter 1 in Daniel Steck's book. So this is going to be Steck 1.1 to 1.3. And just kind of give you an overview of what to expect is that since this is the upper division electronics textbook, the author is not going to have a complete review of the introductory level information, so that from, for example, if you were a Stan State student, that would have been from your Physics 2260 class, which is the second semester general physics, and that's going to be much more detail about what is covered in that class. And the expectation is that you've took that class, and this is sort of like the next level after you finish your general physics course. So I'm going to follow what the textbook does, where it's just going to give you a brief overview. So like each sentence is like one chapter in Phys 2260. So just be aware that what you see here is not going to be complete review. It is expected that you review the previous course or have recently taken it, and that way you're familiar with the material already. Okay, so one thing I want to highlight in this first section, 1.1, is that you have to think about, this is something that maybe I was confused about when I took this course, is that material, right, is generally neutral. So for example, if I take my mouse, right, there's a battery in there, there's some lights and stuff like that. But, right, overall, this, the charge of this entire mouse, if you actually put, a Gaussian surface around this, so hopefully this is somewhat familiar sounding, you're not going to feel electric field coming out of it. What happened is that, let's say I rub this with, a piece of cloth or something like that, and I deposit some static charge onto the surface of this mouse. What will happen is that, let's say those charges are positive, right? What happened is that those positive charge actually will attract the electrons from the air, and those electrons actually will deposit onto the mouse and actually neutralizes it. So whenever there is a excess positive or negative charge somewhere, what's actually probably called thermodynamics will actually neutralize that charge, because of this randomness tends to cause everything to be neutral. So one thing that this is important for us to know is that, let's say you have some conductor, let's draw that in blue, right? Let's say you have some wire, like a piece of metal, right? There's some negative charge in there, right? Let's draw 8 of them. There's a lot more than 8. And for every one of these negative charge, there's actually a corresponding positive charge, which makes the whole conductor 0. What happened is that if you were to apply an electric field to it, let's do that in black, I guess. Or let's say down the direction of the wire, a constant electric field. What will happen is that these positive charge will be accelerated along the direction of the electric field, while the negative charge will be accelerated in the opposite direction. So you're basically kind of pulling these charges apart. The important point here is that, let's say I have a negative charge that moved from this position over to this position, right? After some time that it's been accelerated. But what happened is that this other negative charge actually replaced it. So overall, this little area is still neutral, okay? And then this, where did the negative charge that will replace here come from, right? Remember, this wire is pretty long, so this is going to keep replacing itself. And in fact, in a circuit, all these wires are going to be connected into a circuit or loop, right? So all of these charges actually trying to run around in here, but at any point, the object is actually neutral, because at any point there's, excess positive charge and excess negative charge at any point on your wire. What happens is that the opposite charge will actually come in and actually neutralize it. So that's an important thing to know. So, right, I already mentioned this electric force. This electric force is from this thing called the Coulomb's law, right? So the force of electric is going to be proportional. Well, in this case, you can actually just write the electric field times the charge of that object. But let's say you have a positive charge and a negative charge somewhere, right? You can actually, this electric force is actually going to be this Coulomb constant, the electric constant, charge 1, let's call this Q1, this Q2, right, divided by the distance between them in the direction that these two are away from each other. And actually they're towards each other in this case, because I drew one positive, one negative charge. Okay, so what happened is that, so that's the way to calculate electric force if you have two charges. But if you just have an electric field, this is the way you calculate it. So in going back to this example up here, what happened is that in a conductor, these electrons are actually free to move, meaning they took just a little bit of nudge in order for them to be able to kind of travel along this conductor, and that's what makes a conductor. And this movement of charge is actually what current is. So current, let me write it better down here, right, is how much charge changes. So this is the differential over time. So this is the time derivative of charge. So some of you might have seen this as like Q dot or something like that. So this is not, a bunch of D's, but this is the time, how charge is changing in a particular part of your conductor. And that's what current is. So this is important to note. Okay. In applications of, on circuits, and whenever you build a computer or whatever you're building with this, it's generally not as useful to calculate things in forces. It's actually much easier to calculate things, what is known as electric potential, also known as voltage. But there's one step between the two, between force and potential, and that's the electric potential energy. So what is electric potential energy? The electric potential energy usually is signified by this symbol U with a little subscript E, is basically how much work that the electric field is doing to your particular particle. So the way you calculate work is basically force, right, dotted into some general vector that you're moving this particular particle in. So in this case, right, the force electric is here, right? So this is actually E dot Q, well, E times Q. I'm going to factor out the Q because that's not going to have a path dependence, dot dr. Okay, so that's actually what the what the electric potential energy is. But what's more useful is actually just calculating this this potential per charge, and basically that's how you divide out the charge in this case. So if you divide both sides by charge, so voltage, electric, right, electric potential is basically the amount of electric potential divided by the charge. If you divide out this charge, right, these just cancel, then you just end up with E dot dr in this case. Okay, so this is all good. So this is just kind of useful to have this kind of, fundamental definition of what electric potential is. In the circuits you'll be building, you're actually going to be kind of measuring the difference in potential in different places on your circuit. So let's say, you have some point A on your circuit, and then there's some stuff. We don't even know what the stuff is. And there's a wire that connects them. Okay. and then now you're at some point B. And what happened is that what you're interested in is the difference in electric potential, or the voltage difference between point A and point B. And this is usually signified as delta V between A and B. Okay. All right, so let's see what happens when we apply this to our first circuit element, which is known as a resistor. Okay. And this is where we go into Ohm's law. So, Ohm's law is usually an entire chapter. Actually, basically, the electric force that we just covered is a chapter in your intro class. Electric potential is usually a chapter. Electric potential energy is a chapter. Electric potential is also a chapter. So we already just went through three chapters in the intro level book, because this is stuff that hopefully you've seen and remember before. Okay, so next we go to Ohm's law, which is yet another chapter. So everything that's not made of a superconductor is a special type of material where the electrons no longer feel any resistance in traveling. So anything that you're not dealing with superconductor are actually a resistor. A copper wire is actually a resistor. It has some resistance in it, even though it's much smaller than, let's say, the resistance of a block of glass, for example, which is a very good insulator. So in fact, human has a resistance of about 400 ohms. So if you, when you go to the lab next time, you can actually touch two ends of a ohm meter, and you can actually measure the resistance of yourself. This resistance actually depends on your the ratio of bones, which I think has a high resistance, muscles and fat, and it's actually not the muscles and fats that matters. It's actually the iron in your blood that makes you less resistance, that allows basically charges to move through it. Okay, that's why if you ever have bought one of these fat percentage measuring devices, you can actually, the way they measure your percentage fat in the human body is just by measuring the resistance across you. Okay, or it can also be used to detect iron deficiency, for example. And this is known as an ohm meter because it measures ohms. Okay, it's kind of a weird name for it. I would call it a resistance meter, but historically it's been called ohm meter after this guy Ohm came up with Ohm's law, of course. Okay, so we can try this when we go into the lab. There are different types of resistors. The ones we're going to use in the lab is actually going to be mostly number 2, but let's just go through the introduction of what these resistors are. So the first type of resistor are these wire wound resistors. By wire wound, meaning it's literally just a wire that's been wound up a lot. So it's a long, just imagine a long copper wire, curl into this little configuration, so that's more compact. But if you were just to stretch it out, this would just be a very long wire. Okay. So, and what happened is that you're going to see one end, which is the one of the leads of the resistor, and then you have the other end. And what happened is that the current has to go through this, very, very, very long wire that's inside the casing for your wire wound resistor. Okay, and this is a very good way to make a resistor if you just need something that's very low in resistance. In fact, if you take a 24 gauge wire, we'll talk about what gauge is in a second. Gauge is just kind of like the diameter of a wire. And let's say this wire is a meter long. It's made of copper. Actually, this should be copper. Okay, you actually have about 1/10 of ohm of resistance, which is 1/10 of an ohm is very small. Okay, as you get used to doing more labs, you're going to see, okay, like 1,000 ohm is sort of suitable for a lot of stuff we're using. Something on the order of 10 to maybe 10,000 ohms is what we're using a lot. Basically, a tenth of an ohm is negligible resistance in your circuit, and we're not going to even worry about, oh, how long of a wire did you make in your circuit. Okay, as long as it's, you know, less than a meter, we actually don't really care about it. Okay, the type of resistor you'll use most in your class, in your lab, sorry, are these carbon film resistors. So you're going to see this little picture here. They're, you know, they're maybe the width of your pinky if you're holding it up. Okay. The way these are made is that you have two connectors at the end. So you have a, you know, the current has to flow in and out in one in the other end. But between these leads is actually a thin carbon film. So carbon is actually a insulator in its in its general configuration. You can make graphene sheets of carbon that are actually a semiconductor, but in this case we're just using this as an insulator. So you have this thin film between them. That's an insulator, but it's very thin, so actually some current can jump across it. So what happens is that this will create some resistance, okay? And depending on the thickness of this film, the thicker it is, the more resistance you get, okay? And and these are actually color coded, so we can see that in the lab how we actually decode this. But one way to verify that these things are the resistance you want is actually just plugging into an ohm meter. And these are not the most precise devices, so these are going to be precise up to about 5%, because by depositing just slightly more carbon, slightly less carbon, what happens is that you change the resistance substantially. So they try to make these as precise as possible, but you should not trust these type of resistor down to, you know, at anything less than a 5% level, which is what we're basically going to be using in the lab. There are also the opposite of carbon film resistor, which is metal film resistors instead. So the difference is that instead of depositing an insulator between the two conductors, so you have, you know, you have your two ends of your resistors, what they do is they kind of wrap this around, okay, wrap one of the conductors around, okay, and you make it so that it's a very thin metallic film as opposed to a carbon, which makes it a conductor film, okay? And the thinner it is, the less resistive, the more resistance you'll feel, because now, right, basically what happened is that the electron kind of has to jump this little gap between them in order for the conductor in order for them to travel through the resistor. And this is, you know, basically kind of an opposite way of making a resistor. And these are very nice, but once again, the resistance values of these type of resistors tend to be low, but so in order for them to be, you know, still kind of like, you know, the end of your thumbnail pinky size. Okay, so before we start using Ohm's law, we should probably think about how to calculate how physically these resistance come about. Okay, so this is something you probably learned in your general physics class, but let's just review it real quick here. Okay, so in general, right, resistors or any wires still have some resistance in it. Okay, the longer this resistor or wire, the bigger the resistance. Hopefully that makes sense. So if you have, you know, something that's very skinny and long, right, in order for the electrons to pass through it, right, what happened is that it has to traverse a very long path, which makes it harder, right? And the bigger the cross-sectional area, let's say you have a very large a resistor with a very large cross-section, but maybe shorter, right? So this is area 1, this is area 2, right? You can imagine, well, in this case, more electrons per unit length can pass through it. So therefore, right, so this makes the resistance go down, you know, skinny, long wires makes the resistance go up. So that means the resistance, okay, let's just go over here, right? It's going to be proportional to the length of your resistors or wire and inversely proportional to the cross-sectional area, okay? L is the length of the resistor or wire, whatever you're talking about. And then A is actually the cross-sectional area. Right? Meaning if you stare down the wire, how big that area is. Okay. And then now there's just a constant here, known as resistivity, symbolized with the letter rho. And for each material, it is unique. So for example, if you had copper, the resistivity of copper is about 17 times 10 to the negative 9 ohm per meter. Okay, so the thing you want to think about these units very carefully, right? So if I have a copper wire that's has a cross-sectional area of 1 square meter and has a length of 1 meter, okay, the resistance of that is 17 times 10 to the negative 9 ohms, so which is a very, very small resistance. Okay, usually you don't deal with wires that big. That's a very big wire. 1 square meter wire will be very large. So on a breadboard, for example, what we generally use is going to be these 24 gauge wire that I mentioned before. Gauge is just kind of a weird system of classifying the diameter of wires. So the bigger the gauge means the thinner the wires, which is opposite of what you think. So if you want a bigger wire, you actually want a lower gauge. So the diameter of a 24 gauge wire, so these for diameter, right, is 0.5 millimeter. Okay. That should be a negative. So if you write that in scientific notation, it's 5 times 10 to the negative 4 meter. Okay. So you plug that in to calculating the area of something, right? Pi r squared, right? This is the diameter. You have to divide that by 2 to get the radius. You square that, you multiply by pi. You get a cross-sectional area about 2 times 10 to the negative 7 meters squared. So very, very small cross-section. So let's say if I have a 1 meter long 24 gauge copper wire, right? If I plug it into this equation here, right, the length is 1 meter. The cross-sectional area is 2 times 10 to the negative 7 square meter. Okay. The meters actually completely cancel out. And you multiply by the resistivity of copper. If you do this multiplication, then you get about 0.09 ohms, or about 0.1 ohm. Okay. So that's how I got this number. What is it? Up here, right? About 0.1 ohm resistance on a 1 meter long wire. Okay. So it's very small, right, for a wire still. And in the homework, you're going to see, oh, yeah, if I start running a lot of current through this, there's going to be some problems if you're using wire that are too thin. Okay. When you put your resistor into a circuit, schematically is represented by this zigzag symbol. So I'm just going to draw it. So, you have some place at point A, and the way I draw it is just kind of do a little zigzag here, and I put a little R here, or the resistor value. Or sometimes maybe I'll just put 100 ohm here to represent a 100 ohm resistor there. Okay. So what happened is that, so let's say in this case, right, I have a 100 ohm resistor. Oh, let's do 1,000 because that's what I wrote here. 1,000 ohm resistor. Put another 0 in there. 1,000. Okay. And the voltage between A and B is 1 volt, right? Delta V AB is 1 volt. The amount of current going through this obeys Ohm's law, so the difference in voltage, between A and B is going to give you the current times the resistance value. This is exactly what Ohm's law is, okay? Oops. The H. Okay. So in this case, if you solve for the current, right, you're going to get that the current is going to be 0.001 amp. Okay, so that's the SI units for current. In other words, it's charge per second. Okay, but typically what we write is actually in milliamp. Okay, so this is going to be 1 milliamp, and you're going to see this symbol a lot. So please make sure to know your millis, your micros, and your nanos, and that way, when you see these symbols, you're going to won't be confused by it. Okay. So if you double the voltage across it, okay, you're going to double the current. If you have the voltage, you're going to have the current, because, right, the resistor is a set value. You're not changing that out, right? So basically, the voltage across between A and B, which is across this resistor, is proportional to the current. So if you double the voltage, you double the current. If you have the voltage, you have the current. Okay. One thing that does happen when you're passing current through a resistor is that the resistor is going to heat up. And the way you heat up is a way for it to dissipate the energy that's going to be used in it. The reason that resistor has dissipate energy is because when the electron passes through it, it doesn't actually get to go in a straight line, so it's kind of bouncing back and forth. So this bouncing back and forth actually kind of heats up the entire resistor itself. Okay. So remember that, right? The potential energy, so previously I defined this as kind of the potential energy is the potential, the electric potential times the charge, right? Oh, he's using big Q, but that's fine. I'll use big Q also. Okay. Basically what happened is that as the electron travels through here, it's actually dissipating energy into it. So all of this potential energy gets converted into thermal energy through work, basically. Okay, so the electrons are doing work on this particular resistor, and that's why they changed the symbol from U to W to represent work. Okay, and this is basically the same formulation where the potential is actually just the amount of work divided by the charge itself. We can rewrite this as work being the potential times the charge, just like what we have up here. Okay. If we keep the voltage across this little circuit constant, let's say I'm able to maybe attach a little battery to it, so the potential across it is constant. You can actually differentiate this. Okay. So the time derivative of work, right? I'm just taking the time derivative of both sides of this. Okay. If the potential across it is constant, it comes out in front of the derivative. Okay, that time derivative actually just has the charge. So dq dt, right? Remember the first thing we learned about current is that the change in charge over the change in time is actually current, right? Basically how charges is moving across your resistor. Okay, we can use Ohm's law to basically replace VAB, right? So the power dissipated by a resistor, it can be either the voltage times the current, which is what you have here. Okay, or, right, since voltage across a resistor is IR, right, what you can do is replace this V with I times R. Then you get two factors of I, so it's I squared times R. So one way to calculate the power dissipated. Another way is to replace the current. So if you solve this for current, it's V over R, right? Then you can replace the current in this equation, and you get V squared over R. But it's not super important. I mean, this is just all algebra, so this you can figure out.